Good morning, Fancy Meat Computers. We find ourselves once again in an online space. How are you? Thank you for your congratulations. So the baby has been born. The baby is a girl. We knew that going in, of course, but, still confirmed. It's actually kind of interesting. You don't always get it like a clean hit on the ultrasound, if that makes sense. So sometimes you don't necessarily, sometimes you're surprised, but in this case we were not surprised. So beautiful, perfectly healthy little baby girl. She was born at 12:35 in the morning, yesterday morning. The labor and delivery went extremely well, to the point where we were able to leave the hospital a mere 3 hours later and come home, which was nice because it's more comfortable at home than in a hospital. And it was fantastic. No medical interventions necessary. Just my wife, who is a beast, just had the baby and was a mere, hour and a half later was walking around and just fine, But yeah, everybody's happy, everybody's healthy. It was you couldn't have asked for a better labor. It was at McMaster, actually. We were we were on campus, as it were, last night, or the night before. So her name is Cordelia Shirley Pollard Moore. So her name is Cordelia. The consensus in the Pollard clan is that her abbreviated name is Corey, but I'm still holding out for Dee Dee. I think Dee Dee is a cute name, especially for a kid. But yep. Thank you, everybody. Yep. Yeah. Oh my goodness, I've still got 1MD3 up. Jeez. Yeah, 1MD3 vibes indeed, eh? Oh, that's the midterm. Maybe. Different midterm. That was a different midterm for a different class. Totally was a different midterm for a different class. 2CO3. This is 2CO3. Okay, alright, good. So pursuant to the fact that the child has been born and my services are required around the house a little bit more than is normally the case, because it's if you've never seen a woman and a freshly born baby, it's like they're it's interesting, right? There's kind of this trend lately to call the first 3 months the fourth trimester, because they're although the physical umbilical is no longer connected, you can tell that there's definitely still the spirit of one. But yeah, so I'm required a bit more at home, and will be for the coming weeks. So we're going to be having our lectures online. It doesn't seem like anybody's particularly put out by that, so that'll be good. Apparently half the class failed for 1MD3. Over the summer, yes. Actually, it was 40-45%. Not quite half the class failed. Or maybe I'm wrong. No, I think it was about that much. Yeah, they didn't do particularly well over the summer. That's fine. No, this most recent midterm, no, the average on the first 1MD3 midterm that we had this semester was 75%. So it goes. Which topic will the midterm cover up to? It will cover up to the end of searches. So, no, get out of here. No, thank you. So, the priority queues / binary heap material will be the last material on the midterm. So there you go. Oh, no code is not what we want. We did symbol tables. What am I talking about? There we go. So, so I'm going to assume that no TAs came and presented material on Wednesday. Okay, so we've got questions about the midterm to get out of the way first. This is fine. Okay, so question number 1. Could I go over recurrence relations? Because the textbook has a way of doing it for some complex questions, and the TAs do not know. Yeah, I guess that's fair game. Yep, we can talk about recurrence relations. We do need to make some progress on our, on this stuff. But if somebody could please, tell me whether or not there was anybody there on Wednesday presenting material, that would be good. So, question. Will the format be the same as in previous years? Multiple choice and short answer. Well, it's a different person making the test. In general, the test is like a combination of long and short answer. I didn't really, there are no multiples. There's no, Scantron sheet. It's not there's no, multiple choice per se. There are some questions that are sufficiently short that you may think, if you squint at them, that they're multiple choice because they're very short questions. But in general, no. In general, it's mostly written answers. When it says we have access to the full API of doubly linked lists, can we assume that we have the insert and delete operation? Yep. Do we have to submit our cheat sheet after the test? Nope. Are we allowed to have the same cheat sheets? Highly, highly discouraged, but not illegal. So the problem with using other people's cheat sheets is that what you've done by doing that, whether you realize it or not, is you have given up your most valuable study time and opportunity. In order to create a cheat sheet, what you have to do is you have to go through all of the course material, select those pieces of information which you think are most important, and transcribe them. This is the best studying that you're, among the best studying that you can do, right? So having, using someone else's cheat sheet is a terrible, terrible idea. Do your own cheat sheet. That being said, there's not going to be, any formal penalty or, I'm not going to take it away from you or anything, but let's just say strongly discouraged. The TA did not come in for the 8:30. Okay, so effectively Wednesday's class didn't happen then. In the 9:30 tutorial there was a TA, just not then. Oh, okay. What's happening with SAS accommodations for the midterm? Yes. Excellent question. We'll need to get you guys booked in there to write the test. At this point, I think I won't be able to get the test paper to them in time, so we'll have to have you guys write at an alternative time. Okay? We'll negotiate that, but we do not have time, we don't have enough time booked. We could not book enough time with all these rooms to accommodate SAS accommodations during the actual writing time, so you're going to have to do it in SAS at some point in the near future. Do you think we even need a cheat sheet? Personally, it's like useful for like a couple of things, you know. If you, yeah, like memory aids in general are useful if they're correctly constructed. But you know, if you don't feel you need one, then you're welcome to not have one. For a complete binary tree where each level sums up to n, the slides say runtime would be n log n. The height of the tree is log n, but there would be log n plus 1 levels, so wouldn't it be n times n log n plus 1? So generally these constant terms are dropped, right? So, like, particularly if we're talking about big O, right? You know, if you have n times log n plus 1, or plus anything really, that's going to expand to n log n plus n, and of course with this will be bigger, that's a larger order than this, so that becomes n log n. Maybe that's not your answer, or that's not your question, but yeah. So, is the midterm hard? Not as hard as I'd like it to be completely honest. I think it's a bit of a softball, but whether you find it to be a softball is going to be a different topic entirely. If you studied, it shouldn't be too bad. So, let's see here. Recurrence relations. Oh, we did that in merge sort, didn't we? There we go. So now when it asks for the runtime of a recurrence relation, we should give it the big O runtime. So when it asks for runtime, it means runtime. When it asks for complexity, it means big O. Okay? Is there a pseudocode bit on the midterm? Will we get docked marks if our code is not sufficient of a sufficient format, such as being too Java-ish or too formal? So I've asked you to write pseudocode algorithms a number of times on the assignments, and it's been a major component of the assignments so far, so I would say it's reasonable to assume that there's going to be some pseudocode on the test. Will you get docked marks for it being too Java-ish? I think that you'll find that if you don't have Java in front of you, right? If you're not actually, like, I'm dead certain that what happened in a lot of cases with the pseudocode marks being taken off on the assignment was that people were writing their code in Java and then translating from Java into pseudocode. So it ended up being Java with a few find and replace operations performed. Since to answer the second question, since the midterm is going to be handwritten and not written on your computers, it's going to be a piece of physical paper. I think you'll find that your pseudocode probably won't end up looking very Java-ish unless you're going out of your way to do that. But yes, so in general, pseudocode is a form of communication. You should seek to not include implementation-specific details. So that's what it means when it looks too Java-like. and you should clearly and effectively communicate using your pseudocode, which means not including a lot of redundant statements, right? Using sub-algorithms, right? If you're performing an algorithm on a linked list, it needs to, you have the available options, right? You have your, delete and insert methods available. It's just, like you need to write your pseudocode like you're a real programmer and not just a bedroom programmer that hacks everything together in one file and hacks everything together in one procedure. Proper modularization, my friends. In theory, pseudocode should be so implementation independent that, the difference between a selection sort algorithm that operates on an array and operates on a linked list, for example, should be relatively minor. Mostly it should have to do with the manner in which things are instantiated or, stuff like that. So, I got marks off for translating from Java, but I didn't even do the bonus. Well, that's, I'm not going to listen to complaints about assignments right now. If you are clever enough to write the solution in Java, shouldn't you be able to effectively translate it into pseudocode? Well, no, because pseudocode comes before Java. Like, you've got it confused. You've got it the wrong way around, right? The algorithm gets designed, and then it gets implemented. To produce... So, it's like... So, if you're working for a company developing software, the approach that you are proposing, where you write the Java, then you write the pseudocode from the Java, this is the same as saying, I'm going to write the program and then write the design documents for the program from the program I've just written. You're not writing design documents then, you're documenting an existing algorithm, right? You do the design first, and then you implement it. That is the correct procedure for development, right? To do it in the wrong order is a problem. And it doesn't have to do with how clever you are. It doesn't matter how clever you are. You're eventually going to find programs that you need to actually follow the correct procedure, right? It's like, I don't care how clever you are at math, you still need to show your work, right? So I'm not interested in these arguments about doing the code first and then producing the pseudocode from it. It's wrong and it's bad and you deserve to have marks off for it. So, right. Would it be fine to copy the pseudocode into the Java application and change it to Java? I mean, in general, yes. Although in theory, you should be, like, it shouldn't, like, ideally, it should have, like, copying the pseudocode into, like, a text file and changing it to Java code. Like, the pseudocode should be implementation independent enough that you'd be just as well off just typing it up. Like, rather than copying and pasting, like, having your pseudocode on one half of your screen and your Java code that you're working on the other half, and, you're reading this and doing a little Java, reading this, doing a little Java, right? Like, if it's copy pastable and all you have to do is a few find and replaces, then, that's also not good pseudocode. Yeah. So, on the slides it says dn is equal to n log n, but that's big O, complexity, not exact runtime, which would have... when is there a difference? Let's see. Maybe the problem is this +1 that you guys have, that you guys are talking about. So, so the depth of the tree, right? Let's just so I'm gonna do this with like base 10 stuff because I'm not sure how to get the base 2. So log 1, right? That's height 1, right? Yeah. Log 10, that's level 1. Log 100, etc. Right? So the height levels are 0, 1, 2, 3, etc. Right? So the height, like, in general, like, I don't know, like, I didn't do this diagram, I'm taking this on the authority of the textbook, right? But, this is, so, this might be the clue right here. So if d at 1 is 0, right, then at the d at 1 level, that whole level would still be summing to n. So you have n, yeah, you have n times log n plus 1. So let me think about that one, okay? I'll get back to you on that one. Because, you know, looking at it, I think you're right that the timing function would be different than what's stated on the slide. Are many of the questions going to be requiring us to write pseudocode on the midterm? There will be some pseudocode, certainly. Can pseudocode assume stuff like pass by reference? If you're making assumptions like pass by reference, pass by value, you should state that in the pseudocode. State your assumptions. Can we write log in the midterm instead of LG when talking about the complexity and runtime? No, log, LG. You either write LG or log with a subscripted 2. Alright? Log with no subscript is base 10. Can you explain the top part with the fractions? No, we need to cover new material today. Yeah. We need to cover some new material today. We've talked about the midterm long enough. So, on Monday, we were talking about 2-3 search trees. All right? In general, binary search trees are an extremely effective method of organizing data in such a manner that you can search through it quickly to find a particular element, right? It's logarithmic time searching. Generally speaking, once we're in logarithmic time for anything, we're kind of in the goal zone with respect to computational complexity. However, the binary search tree is only logarithmic on average. The worst case runtime for the binary search tree is still linear, which we'd like to improve. Um, the reason for this, of course, is that a worst-case binary search tree is simply a single branch, a tree composed of a single branch, wherein all nodes are in one branch. And what we want to do is we want to come up with so-called tree balancing algorithms, which allow us to address that worst-case scenario. Basically, we want a way of performing insertions and manipulations on the tree which will result in the tree not having different branch levels. If we can keep all of the branch levels the same, then we have successfully addressed the worst-case runtime. Our first algorithm, we're going to look at 3 ways of doing this. The last one only briefly. 2-3 trees are sort of your basic way of approaching this problem. It's extremely clever, these things. In general, just briefly summarizing, 2-3 trees will contain either 2 nodes or 3 nodes, right? 3 nodes, rather than... So in a 2-node, it is just exactly the same as a binary search tree. You go down the left branch for less than, right branch for greater than. If you have a 3-node, that contains 2 values, and these nodes have 3 children. That's why they're called 3 nodes. Rather than being a simple test of left and right, it's is it less than this interval, greater than this interval, or between or inside this interval? Good. Fine. So, searching is exactly how you might expect it to go. Very simple. However, the big thing about 2-3 trees, that the thing that makes them work, is the manner in which we are inserting values. So the reason we get into trouble with binary search trees is that nodes are inserted at the ends of branches, and there's no correction or balancing that goes on to address long branches. So insertion in a 2-3 tree is very clever because it decouples the tree growth from the node add or the value adding procedure. So when the tree grows, it grows in a different location than where the value is added. So you can kind of think of it as values are added to the branches in such a way that the branches absorb the new values, and when they grow large enough that they can no longer absorb the values, they send those values back up the tree and expand those values up the tree as they go up. Right? So we've got these binary search trees. There are a lot of different cases that we're going to examine, but all of them follow the same procedure and philosophy. It's like, while memorizing the individual cases is good, understanding the philosophy which governs the behavior is much better. Because then, in theory, you could derive each of these cases if you have a decent understanding of the philosophy. Right? So, let's say we have this guy and we're inserting k. We first find the position at which k needs to be inserted, which is adjacent to this L. Actually, I've got the ability to draw here. Let's see here. Yeah. So, have I got hotkeys? I do have hotkeys. All right. So, we find our way down the tree. We find that we want to insert right here. So, because this is only a 2-node, it has room to accept another value. So, we add the value to this node, expanding it to a 3-node, and everything's good. And this is, like, no matter where the node occurs, a 2 node can always be expanded to a 3 node with no fuss, no muss, no problems. The problem comes when we need to insert a value into an existing 3 node. So if we have the following situation, we've got A and E, and we want to insert S into that. Were we to perform the insertion, we end up with what's a temporary 4 node. So 4 nodes exist, they exist in a temporary way, and like if you were producing a data structure or like a Java implementation of this, 4 nodes don't actually exist, right? Like if you have a class for 2 nodes and you have a class for 3 nodes, your algorithm does not require 4 nodes to be a class. You don't ever have to store them in memory because they are, as soon as they are created, they are instantly decomposed, right? They're kind of like unstable isotopes. So 4 nodes have 3 values and 4 children, as you might expect, and it works the way that you would expect the intervals to work, right? There we go. This branch would be everything less than A. Oh my goodness, trying out different things. This would be between A and E. This branch is between E and S, and this is greater than S, right? So what happens when a 4 node occurs, because they are unstable, they are immediately decomposed into a 2-3 tree containing 3 new 2 nodes, arranged in the following manner. So if you think about the intervals going on with the children, right? This branch is still going to be still going to be less than A. This branch is still going to be between A and E, although E is tested first. This branch is still going to be between E and S, and this branch is still going to be greater than S. So what's very, very important about this transformation, none of the children are affected. We don't have to propagate any changes down through the tree. This is a local transformation at the level of the 4 node with no requirements at any other level in the tree. This is extremely, extremely good. Right? So how do we know we want to make something into a 3 or 4 node rather than just add a leaf lower down the tree? Because you never add leaves down the tree, right? Thank you for the question, Oliver. That's an extremely important point. In a 2-3 tree, you never, ever, 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 ever add a leaf at the bottom. You never do it. Not even once. And we're going to see why, right? Because you might be thinking to yourself, okay, sure. If you never, ever, ever add a node, how does the tree grow, right? If we never add nodes down here, how does the tree expand, right? And the answer is it expands from the root. So let me finish my description here. So when we take a 4 node, it splits into this type of configuration. However, if this expansion happens, we don't simply create a node in the middle of this branch, right? That would be to expand this branch, and we don't want that. So if we have a parent node, the middle value that's popped out, right, that gets added to the parent, right? And the same rules apply. In this particular case, the X node is added to R to create a new 3 node containing R and X, right? So this middle value gets popped up to the next level of the tree, right? The generated parent node is quickly added to its own parent. This may make the parent unstable as well, so this procedure follows the tree upwards until it hits the root node. If the root node decomposes into 3 2 nodes, there is no parent to merge into. Therefore, the new branches add to the depth of the tree. So, thus 2-3 trees can only be expanded at the root, maintaining perfect balance. So, for example, here's an example where we are passing things up to the level of the root, right? So we're inserting D, that'll go at the end of this interval. C is going to be popped up. We make the temporary 4 node. We pass up the C, right? That C creates its own unstable 4 node, so we pop the middle out and pass it up to the root. In this case, the root becomes a 3 node, right? So, good, so far as it goes. Not adding nodes to branches, root nodes expanding evenly, perfectly balanced, as all things should be. Oop, oh no, what did I do? There we go, all right. So, and do I have a slide on? Okay. Somehow I managed to not have a slide that depicts the root node expanding, so I'm going to do it in Krita, which is kind of like Linux Paint, but much better. So, I apologized for the hand-drawnness of this, but so it goes. So let's say we have a very small one, right? Let's say we have a Z, right? We'll say that, like, A minus is, well, actually, I don't even care. That will go off to do whatever. We'll have one over here that goes off to do whatever. It's a little small. Let me increase the pen size a little. So let's imagine we have another guy here, right? B and Y. Let's imagine we're adding M, right? So when we add M, the correct place to add it is right here. This creates an unstable temporary arrangement, right? So this guy becomes A here. M gets popped up and passed into the middle of the node above, right? And then we have the whatever branch on this side, the whatever branch on this side, B and Y. It's good so far as it goes, but we now still have an unstable 4 node, so this is how that works. This guy, the middle gets popped out, but there's nothing to add it to, so it just hangs out here. It's a new 2 node. It has 2 subordinates, A and Z. A receives the 2 left children, Z receives the 2 right children. The reason I have dots here is I realize I painted myself into a corner by making these A and Z. Because, like, what letter is less than A? What letter is greater than Z? Stupid. But, so you can see that through this operation, the height of the tree has gone from 2 to 3, right? But this, like, although these are going off to dots, it's actually, like, there's only one node here. It might be a 2 node or a 3 node, but there's only one node on each of these branches. So you can see the tree has only expanded up. No branches have been added to the bottom. We still have this perfect pyramid shape. Right? Does that make sense? Give me a thumbs up if everybody... Give me a thumbs up if you understand what I'm talking about. Good. Wonderful. So, in terms of programming, right, once you get into actually trying to produce an implementation of this, there are only a fixed number of situations you can be in that cause... there are only a fixed number of ways that 4 nodes can decompose, right, depending on where they are in the tree. If they're in the root, of course, we decompose into that structure. You can see we add to either the left or the right of the interval, depending on how we are, when the parent is a 2 node, and when the parent is a 3 node, we always produce another 4 node, but the question is, where do you put the middle value? And it's, you know, reasonably intuitive if you understand where the intervals are coming from. But this means that basically, when you code this up, you have 6 cases that you need to deal with, right? Which is not a huge number of cases, but, you know, still some number of cases. So each transformation maintains symmetric order and perfect balance, right? So every single time the tree is transformed, both branches are transformed, like, symmetrically. Because everything is always symmetrical, and because the tree only grows at the root, that's how we maintain our perfect balance. And the reason the perfect balance is the perfect balance is the whole point, right? Because the problem with BSTs that cause the linear worst case runtime is the fact that there's no guarantee of balance. Here, balance is maintained by construction. It is impossible to have a 2-3 tree that's not balanced. And while it does take more time to test these, you know, intervals rather than single values, and, you know, while it's somewhat cumbersome to do the insertion procedure itself, because the insertion procedure at maximum pushes a value from the furthest extremity back up to the root, that is also just a logarithmic operation, right? That's also a log n operation. So, in general, we do quite well. Every path from root to a null link has the same length. In the worst case, the tree height is log base 2n. All nodes are in 2 trees. In the best case, we actually have log base 3n, which is approximately equal to 2.631 log base 2n. All nodes in the tree are 3 nodes. So because we now contain either 1 or 2 values in each node, the number of nodes, or the number of values the tree contains, can no longer be directly calculated from the number of nodes in the tree. But this turns out to not be a terribly useful property anyway, particularly when we're gaining logarithmic runtime. So, in terms of our symbol table implementation, direct implementation is complicated because maintaining multiple node types is cumbersome. You need multiple comparisons to move down the tree. You need to move back up the tree to split 4 nodes, and there's a large number of cases for splitting. In general, this is still pretty good, though, right? Sure, you have to do some extra bookkeeping, and, you know, you have to maintain multiple node classes, right? But, in general, it works, and it works quickly, and it's balanced, and it's fair, and it's everything that's nice, right? Our constant C depends on implementation, but our guaranteed search, insertion, and deletion times are log base n, C log n across the board. And this is also true in the average case. So, the 2-3 tree is an improvement over the BST. Although, you know, it's kind of interesting, right? Because in this class, it's like the actual implementations of most of the algorithms that we've talked about so far have been relatively simple, right? The code fits on one slide for pretty much almost every procedure we've talked about so far, you know. And of course, the slides have a tendency to write in an extremely condensed manner and like do one-line loops and one-line if statements and that sort of thing. But in general, if you can compress it down to one slide, it's not that long an algorithm. This algorithm would not fit on one slide. There are too many cases to examine. There are too many classes to examine. This is not, you know, this does not mean that you couldn't usefully address these issues, right? Just, you know, that's just how it goes, right? Make sense? Are there any questions before we move on to red-black trees? Is that the baby crying, or am I hearing things? That's the baby crying. That's DD. During the midwife has been at the house this morning, and I'm not sure if the midwife is still here actually, but one of the things that they have to do in the first 24-48 hours is take a blood sample, which requires like pricking the foot and massaging the foot to extract droplets of blood in the same way that you might take a diabetes test, like a blood sugar test for like diabetic testing strips type thing. So you can imagine she wasn't a fan. But no questions. Okay. Well, I do have a couple of questions. Seems to me that you should ask those questions, and we'll save red-black trees for next class, eh? Are your questions about the midterm? I imagine they might be. BST equals balanced search tree or binary search tree? BST stands for binary search tree. Is this at all like a binary heap, where the better average case might not be worth the extra constant term? Like, we're not stopping here, right? We're not, Pardon me. So, sorry. This, so 2-3 trees, we're not stopping here. Red-black trees are an improvement on 2-3 trees, right? So are we in a place where you would use this over a regular binary search tree? Perhaps not just yet. It depends on, like, how worst case your data tends to be. You know, like if you're in a situation where you know your data tends to come in like a roughly sorted manner, then it would be worth doing a 2-3 tree, even if it's slightly less efficient for some things than a binary search tree. But yeah. So I asked the TAs, and they said there's multiple choice. What happened? I wrote the test, and then it ended up not having multiple choice on it. So there you go. That's what happened. What happened is between the TAs getting that information and now, the test was actually produced. So there you go. Can we go over n squared, or cn squared? Yes. So it should be reasonably obvious if you do the if you do out the diagram, right? Let me just where are we here? Where was it? Yeah. Something like this. Right here. So will the tutorial solutions be posted before the midterm? Nothing will be done before the midterm except me getting the midterm photocopied. So, with respect to, like, just kind of an intuitive sense, right? And your intuition about this should be, if my constant term is n squared instead of, or like if my non-recurring step is n squared, all of these n's will become n squareds, right? Which will change how things, basically that'll carry through and you'll get a squared here, right? That's your sort of intuitive setup. With respect to the solving of the recurrence equation, right? Yeah. That's for height. Let me just answer this one. So So the question we're answering here is, like, essentially, right? Yeah. So if we examine this example, right? solving for path height, solving for everything. We've got our divided array, right? The largest subarray dictates the tree height, right? At the maximum depth, n over whatever the fraction is to the power of h is going to be equal to 1, where h is the maximum tree height. So you solve for h, right? Each level of the tree takes c times n, so with h levels, the total of time is going to take is big O n log 10 over 9n, right? So there you go. Wouldn't the cost of each level be different? Yeah, you'd have to factor in like so yeah, I can see why you're on this point. So so the question then, right? What happens if it's n squared that's going on, right? Because like the thing that's going on here, right? If this function receives d at n over 2, right? When you sub that into the recurrence equation itself, if that's getting squared, right? Then at the second level, you would have 2 times n over 2 to the power n squared, this guy, shall we say, to the power of 2, right? Which would be equaling n over 2, not n, right? So in fact, what ends up happening is you have n over 2. If you do the next one, it'll be 4n to divide by 4 to the power of 2. So you would have, sorry, I need a square there. So n squared over 2, right? The next one would be n squared over 4, right? So, so essentially, you can generalize that to n squared over 2 to the power of the current height, right? So, you have to take that equation, and that also that factors in where you're into this equation here, right? So at the maximum, right, you have to take into account, you know, so you've got that, right? You get a maximum depth that's also dependent on h, and you have to like you have to do some algebra on that, and I'm gonna leave it there so that you guys have let's see here. Yeah, the TA flip-flop saying this was the way, but the textbook would go different. Can I do a problem from sample midterm? No, it's this isn't like open season, guys. I'm gonna have to leave pretty soon. Yeah. I'm sorry to leave a bunch of unanswered questions in the chat, but I have to go now. I can't just answer these all afternoon, so put your questions in Piazza. I'll ask the TAs to take a look at them. Okay? Take her easy, folks.